Okay, welcome to week 6 of Case Studies in Scientific Literacy and week 2 of our module on climate change. Okay, so here's the outline for our module. Spacebar up here. Okay, sorry about that. Okay, so we talked about the fact that a lot of people are still really skeptical about climate change. So did any of you, I heard that some of you took these quizzes and were maybe a little surprised at your results. How about your climate profile? I don't know want to know what you scored. That's not my business. But were you surprised by your score? No. Extremely alarmed? Okay. Were you surprised by your score? Oh, okay, sorry. Don't mean to put you on the spot. So, like I said last week, when I took this, I actually still am kind of surprised at my score on the climate profile. But last week we talked about the evidence for the fact that there is global change. So this week we're going to talk about, so we talked about is climate changing. This week we're going to talk about what is actually causing climate change. And we're going to start back a really, really long time ago. And we're going to talk about a wide range of time in Earth's history. Because climate, as we saw last week, climate has actually been changing. It's dynamic. So here were some of our lines of evidence that things are changing. Global change. What did you find most convincing, or what did you find least convincing? This is question and answer is hard to do when we have only 2 students, but if you have something like on the top of your mind, what do you? Okay, glacial retreat is really convincing.
For me, ocean acidification.
Ocean acidification is convincing. Okay, cool. So you might imagine that some of those lines of evidence maybe aren't as strong as others. Some people might be skeptical of some of those data sets. So this week we're going to talk about what is actually causing global change. Now, to do that, we need to have a crash course on Earth's climate system. So what are the parts that make up climate? And we're not talking about weather, because that's something else. We're talking about climate. And then, once we talk about what is Earth's climate system, then we can start talking about what are some of the natural drivers that change the climate system. And then next week, we'll actually get into the anthropogenic drivers. How do we know that we're contributing to this change? So today, we're just going to talk about natural drivers of global change. So, components of Earth's climate. Okay, so the parts of the global climate that I'm going to talk about are the atmosphere is really important, the hydrosphere or water, and here we're mostly talking about the ocean because it is most of the water, right? And then land surfaces. And we'll also talk about some of the interactions of all of those. So we have the atmosphere, we have water, we have Earth's surface, and these things contribute to Earth's global climate system. So, starting with the atmosphere. When the Earth was first formed 4.5 billion years ago, the Earth didn't have an atmosphere. You guys might have talked about this kind of timeline in the evolution module. So we didn't have an atmosphere. Single-celled life appeared about 3.5 billion years ago, and microbial photosynthesis started producing oxygen. An ozone layer developed about 600 million years ago, and that was really important because it prevents UV or ultraviolet radiation from reaching the surface, which before that was preventing the development of life, especially on land. So once that stratosphere of ozone developed, then terrestrial life started to evolve, including terrestrial plants, and so then we have this continued buildup of oxygen in an atmosphere. So if we look at the atmosphere over time, back, a long time ago, we don't know. And then various parts of the atmosphere started to evolve, and finally we have oxygen and nitrogen primarily. So right now, our atmosphere, oh, you guys can't see that, there. So right now our atmosphere is about 78% nitrogen, a very tiny percent of carbon dioxide, but we'll see that that is important. Oh, okay, sorry. What I'm seeing here and what you're seeing here is not always exactly the same. Water vapor. At sea level, there's about 1% of water vapor in the atmosphere, and we'll see in a minute that that can change by location. Maybe here in Florida, there's a lot more. Okay, so the atmosphere does a couple of things. The atmosphere protects the surface of the Earth from ultraviolet radiation, right? And it also absorbs and emits infrared radiation or heat. So the atmosphere also keeps our Earth from being cold. If there was no atmosphere, it'd be really cold or really hot, depending upon which direction you're facing. So protecting the Earth from radiation and absorbing and emitting heat is really important. So the energy budget of the Earth needs to be balanced. So we have radiation coming in from the sun, solar radiation. We have heat radiating back from the Earth's surface, and some of that is being captured by the atmosphere. Some of it goes back out to space. So this needs to, the incoming and the outgoing needs to be balanced. So here's a breakdown of sort of energy in, energy out in random units. It doesn't really matter what they are. But we can see here that there is some energy that is absorbed by the atmosphere. So that energy absorbed by the atmosphere is really important. And what is actually absorbing that energy are called greenhouse gases. They're basically gases in the atmosphere that absorb the energy and prevent it from going back out to space. So these greenhouse gases actually capture about 70% of the energy that is radiating back off of the Earth's surface. So that, again, is keeping the Earth warm. So what are these greenhouse gases? So again, they absorb and emit radiation in this heat range. And they include water vapor, carbon dioxide, which we'll hear a lot about. It's often the greenhouse gas that we hear about. Methane, which is really important also, nitrous oxide, ozone. So those are all natural things. And then we have a man-made thing, chlorofluorocarbons, which we'll talk about next week. Okay, so water vapor and carbon dioxide are the most abundant greenhouse gases, as we saw in our atmosphere concentration graph, right? And if we look at these greenhouse gases, it's actually pretty interesting. So the concentration of water vapor and clouds varies a lot, you know, so it's anywhere from 10 to 50,000 parts per million. And that contribution is highly variable. Now, water vapor lasts in the atmosphere about 9 days, so it kind of has a half-life, basically, or a lifetime of about 9 days. Carbon dioxide, remember, that is a really tiny amount in the atmosphere. It's about 400 parts per million. So it has a relatively small concentration, or contribution to greenhouse gases, maybe 9 to 26%, but it has a pretty long lifetime, 30 to 95 years in the atmosphere. And then we go down from there. Methane, 1.8 parts per million, and 4 to 9%, a 20-year lifespan. The thing is, though, that although, and we'll talk about this next week, because methane, even though it's very, very tiny amount, it's a really, really strong greenhouse gas. And that becomes important when we talk about how we know that it's a human contribution to climate change. Okay, let's talk more about water vapor. So here we've got our, well, first off, we're going to talk about water. Sorry. So the hydrosphere, mostly the ocean, but also lakes, rivers, whatever water is on the earth. So one of the things that the hydrosphere does is contributes to the water vapor in the atmosphere, right? It's also a reservoir of dissolved gases, including CO2, or carbon dioxide, a greenhouse gas. Land surface. I don't know what, there's some weird thing, I don't know. Okay, because, so land surfaces. Land surfaces, when you've flown in an airplane, right, you look down at the earth, and different parts are different colors, right? We have dark surfaces and light surfaces, everything in between. So dark surfaces, actually, like a dark dog. I was just talking to a friend whose dog overheated because he's black. They absorb solar energy, right? So dark surfaces on the earth absorb solar energy and re-radiate that back as heat. Light surfaces just reflect that energy as short wavelengths back to space, and it isn't re-radiated as heat. So that is going to be important. This reflectivity is called albedo. It's the amount of solar radiation that is reflected from a surface. So if we take the Earth as a whole, the Earth's albedo is about 30%. What do you think the relative albedo of these different land surfaces might be? So forest, soil, sand, ice, snow. Which ones are going to absorb heat? Which ones are absorb light and re-radiate as heat? Which ones are just going to reflect that solar energy? What do you think? Which ones are the most reflective?
Ice and snow.
Ice and snow. Yep. How about least reflective? Yeah, forests and soil. So the relative albedos of these different land cover types range from snow, which is highly reflective, to forests, which are absorbing and emitting a lot of radiative heat. Okay, so there we have our albedo contribution to this, how much is absorbed and how much is radiated back out to space. So actually cloud tops are also important in reflecting energy back to space, snow and ice, and the atmosphere. Okay, so we've got these three components of climate: atmosphere, hydrosphere, land surface. Now I want to talk about some natural drivers of change in this climate scenario. So we looked at this last week, that Earth's climate has been dynamic. It's been changing. So what components of this might alter that system? Changes in solar input is a natural driver of global change. Volcanic activity is a natural driver of change. And then we have various interactions of those with the atmosphere, with the hydrosphere, with the land surface. Okay, so first I want to talk about changes in solar input. So changes in solar input have been happening since the Earth came into being. So let me see, we need to do the video now. So we're going to watch this video about Milankovitch cycles, because I'm really bad at explaining them. And this video does a pretty good job. Now the words go, they flash the words up too quickly, so I'm going to try to pause so we can read better what it says. And it did have some pretty good music with it, but we've taken that out. But I have the YouTube that you could actually go and watch it if you like. Okay. Okay, so Milankovitch cycles. The Earth has cycled through hot and cold periods known as glacials and interglacials. We saw in that previous graph there have been cold periods and warm periods, right? Where do I click to get it to go again? Oh, okay. So Milankovitch cycles are what has been causing these series of glacials and interglacials. And it's due to the Earth, changes in the Earth's orbit. And there's three different things that are interacting that causes changes in the Earth's orbit. So we have precession, eccentricity, and tilt. Okay, so first he's going to show eccentricity. So this is basically that the Earth's orbit has been changing from circular to an oval in cycles of about 100,000 years. Did I miss something? Okay, next he's going to talk about tilt. So the Earth is also, I meant to bring a ball or something. The Earth is also tilting on its axis. Just a little bit, but it's enough to bring the northern hemisphere a little closer to the sun, or a little more pointing towards the sun. On a 41,000 year cycle. Okay, so precession is kind of, okay, so precession is kind of the Earth is doing this kind of thing. And again, it's sometimes pointing the northern hemisphere more towards the sun. So these are cycles that are happening on 26,000 year cycles, 100,000 year cycles, 41,000 year cycles. And I clicked too many times. I was going to ask you, what are the implications of these changes in solar input? But here's the answers. So, as a result of these different cycles, we have varying inputs of energy to the Earth from the sun. And because the northern hemisphere is maybe pointed towards the sun more or less, we also have more or less ice in the northern hemisphere. Very cool. Okay, so first let's talk about the implications of having varying amounts of energy input to the Earth from the sun. So one of the things that happens, so this is kind of a general carbon cycle, which if you're a microbiologist or a horticulturist, you probably know about the carbon cycle. So basically we have plants that are respiring, they're photosynthesizing, we have microbes doing things with carbon, we have respiration and photosynthesis taking place in the oceans as well. So we have a carbon cycle. And because there are changes in solar energy, we actually get changes in this carbon cycle. It might speed up or slow down, right? We get changes in the amount of CO2 that might increase because of respiration or photosynthesis. And we get feedback between the CO2 and temperature. So as temperature increases, things speed up, we might get more or less CO2, right? So we get changes in the carbon cycle. We get carbon cycle rate changes, and here we can actually see temperature as well as carbon dioxide, and we see that they're related. So we get changes in the ocean and atmospheric CO2, and then we get this feedback between carbon dioxide and temperature. Changes in solar input causing changes in ice in the northern hemisphere is really interesting, I think. So we've got a interaction between the land surface, ice, and the atmosphere and solar inputs. So remember we said that ice and snow are highly reflective, right? So what's going to change if we have increased energy input to the northern hemisphere? We're going to get less snow cover, less sea ice. Remember we talked about the sea ice last week, which is going to change the reflectivity. We're going to get water, maybe open water instead. We're going to get more forest or more land that's less reflective. So we're going to get changes in the extent of snow and ice in the northern hemisphere. which result in changes in reflectivity and albedo of the northern hemisphere and really the Earth as a whole. Which is, I mean, it's fascinating. It's really cool. So that means that we're going to have changes in the amount of energy that is reflected back to space or absorbed. So we have less snow, less ice. We're going to absorb more energy, reflect less back to space. And then we kind of get this like feedback loop, right? Because we've absorbed more energy, things warm up, we get less snow and less ice. So that's one of the things that has changed over time with these glacial and interglacial periods. Volcanic activity is also important in structuring the atmosphere, and it's a natural driver of global change. Volcanic activity. So here I am a few years ago at Crater Lake when my kids were much smaller than they are now because they're like this big now. And remember the cartoon graph timeline I showed you last week? So here's massive volcanic eruption in Oregon creates Crater Lake at about, I don't know, I can't read the timeline, but anyway, it's on the timeline. I thought that was kind of cool. Mount St. Helens is another example. I was actually in high school when Mount St. Helens blew up. We had ash at my house. It's very exciting.
Where'd you live?
Near Seattle. So, I mean, probably 100 miles away, maybe? Yeah, it's very exciting. Okay, so we've got our massive Crater Lake, and we've got other volcanoes, right? And so what volcanic activity does is it increases dust in the atmosphere. And also it increases, they actually spew out CO2, right? Also a greenhouse gas. So we've seen this graph before, but we were just looking at temperature. But here we have a graph showing dust as well. And what kind of associations do we see? Well, it looks like when dust increases, we get a drop in temperature. And in fact, going back, not that long ago, 1880, we can look at various eruptions, and there are actually little blips in the Earth's temperature, which is amazing. So, here's Krakatoa, or however you say it, and there's a dip in temperature. And again, why is that? Because we get dust in the atmosphere, which limits the amount of energy, solar energy, actually reaching the Earth. So volcanoes are another factor, another natural factor that has changed Earth's climate over time. Okay, we've got the hydrosphere, and we've got interactions of the hydrosphere with the atmosphere. So what happens to maybe a water cycle? So we've got precipitation, runoff, evaporation from the hydrosphere back to the atmosphere. What might happen as global temperature increases or decreases?
Probably like maybe an increase in evaporation.
So like the carbon cycle, the water cycle actually slows down or speeds up. So we get changes in water vapor, which is a greenhouse gas. So if the cycle in temperature increases, the cycle speeds up, we're going to have more water vapor in the atmosphere, which is a greenhouse gas. We probably also get changes in cloud cover, which, wait, cloud cover reflects energy, but probably not uniformly over the Earth, right? And another important thing, so this is water vapor over Boulder, Colorado, that you can look at your favorite place if you go to this website, which I didn't put up there. And just since 1980, the water vapor in the stratosphere over Boulder has increased 1% per year. So I mentioned cloud cover. Like, why isn't that important? Well, so this is measuring water vapor in the stratosphere, and clouds are like way down here. So water vapor is absorbing that heat and keeping it, on the Earth, where our reflective clouds are way down here. So the water vapor is really important. Okay, so last week we talked about various lines of evidence that the global climate is changing. Now, most of these have to do with, temperature and warming and loss of ice and so on. Another thing that I mentioned is sea level rise. Now, sea level rise has also been changing over the course of the Earth, right? So why is sea level rise dynamic? That doesn't really have anything to do with climate, does it? So we talked about some natural drivers of change, feedback loops of carbon cycle and albedo and water cycle. But let's talk about this sea level rise. So last week we talked about the fact that there's been it's risen dramatically in the past. If we look at, thousands of years ago, maybe sea level rise not that exciting. Doesn't seem that dramatic. But I want to talk about this ice because, look, we have final collapse of North American ice sheet. Leads to rapid sea level rise. And then we have some cooling, and then we have some other, the seas rise to near their modern levels. But we also looked at this graph that showed that more recently, sea level rise is accelerating. So sea level is still rising, and just in the last few years, that rise has accelerated. We also learned that the heat content of the oceans is increasing. And part of that is actually due to thermal expansion. So this has been, again, something that has been happening over the course of the history of the world. So it gets hotter, it gets cooler, the waters in the hydrosphere expand or contract. So we know that, for example, changes in water, as you increase the temperature of some volume of water, it gets bigger, right? Thermal expansion. So this is happening in the oceans too. As the oceans heat up, that water is expanding. Okay, so we have thermal expansion increasing the size of the ocean, so it's going to go up on the shorelines, right? But we also have loss of land-based ice. So this is just a graph showing the contributions of different parts of loss of land ice. So this is, for example, this is the sea level rise, and we have contributions of Antarctic land ice melting, the contribution of Greenland ice melting, all ice that is melting, mountain glaciers melting, and so on. So, loss of land-based ice is also contributing to sea level rise. We talked about sea ice. Do changes in sea ice contribute to changes in sea level? So the dogma has been no. If you put an ice cube in a glass and let it melt, it's not going to overflow, right? I mean, it's water. It's in the water. It's not going to go anywhere. But some scientists are starting to question that. So these people published a paper, "The melting of floating ice raises the ocean level." And they actually, this cracks me up, because they actually did, some little experiments, and including melting ice in water, and published this picture. So what they did was they have the ice cube in a glass of colored water. They let it melt, and indeed the water rose. How is that possible? So what we have in the oceans is we have freshwater ice cubes. We have freshwater sea ice floating on top of seawater. And because of the salt differences, the freshwater ice is going to float higher than one might expect. So when it melts, it really does contribute to increasing the volume. And they calculated that if all floating ice and ice sheets melted, sea level would rise by 4 centimeters. So that doesn't really seem like that huge of a contribution. So does sea ice contribute to changes in sea level rise? Maybe a little bit. Where the loss of sea ice becomes really important is that sea ice is actually buttressing or keeping land ice on the land. So here we have some sea ice floating on the ocean and some land ice being kind of held up by this floating sea ice. And we take that floating sea ice away. I don't know where these little black squares came from. We take that sea ice away, and now this land ice is free to just like slide on down, right? So it accelerates the loss of land ice also. And we saw this last week, this sea ice next to, for example, Greenland, which has land ice. And again, we're seeing that these ice sheets on land are being lost. Okay, so sea ice is also important. If you had a chance to play around with this website, last week I showed this picture because here we are in Florida, and sea level rise is about 20% greater than the global average. Almost scary. But if you explored this website a little more, you might find that, oh, sea level rise isn't the same everywhere. In fact, sea level is going down in some places. How is that possible? So that's the result of a few things. Tectonics, so the land is actually shifting up or down, right, which will make it appear that sea level is going up or down. Sedimentation, so for example here at the Mississippi River Delta, we've got tons of sediment coming out, so that results in it appearing that sea level is rising really rapidly. And we also have glacial isostatic adjustment. So this is one of the reasons that sea level has been changing over long periods of time. So we've got these glacial periods, right? We've got glacial periods. Earth's temperature is dynamic. We've had times when it was warmer and colder than present. So we've had glacial periods in the history of the Earth. What does that have to do with sea level rise? Well, ice, we've had ice and glaciers all the way down to, so here's, New York with ice as high as the Statue of Liberty. We've got ice covering where Boston is. So we've had periods in the Earth's history when there has been ice, pretty far down south. So what is this isostatic adjustment? I put a picture of a leather couch up here. What happens when you sit your butt on a leather couch? You sink down, but what else happens? It puffs up around you, right? So it sinks down and it puffs up around you. The same thing happens with glaciers, glacial ice. So ice is really heavy, and if you've got ice up to the top of the Statue of Liberty, that's a lot of ice, and it's really heavy. So it actually squishes the crust down and the mantle where it is and kind of puffs it up where it's not, right? And then what happens when that ice melts? So the crust of the Earth and the mantle is very fluid. It's going to start popping back up, but of course it takes a really, really long time. And that's why we get vertical velocities of the Earth itself moving up. So all this area here is still popping up since the last glacial period. It's called glacial rebound. So we've got glacial rebound, which results in coastal areas appearing to have sea level drop. But it's because the land is still popping back up, right? But overall of the Earth, in general, we have sea level rise because of all these other changes that I talked about. Okay. And we've also got, interactions of these solar input and so on with sea level rise. So that's why I include sea level rise in talking about some of these long-term global changes that have been happening. Not necessarily climate, but it interacts with climate. Okay, so next week we're going to talk about this little blip at the end. The fact that some of these changes are accelerating, and how do we know that humans are the cause of that acceleration in changes that have been happening for millennia but now seem to be increasing. So we've talked about natural drivers of global change, and next week we'll talk about anthropogenic drivers of change.